Alright, let's continue our discussion about direct variation. Last time we looked at direct variation of the form y equals kx, where we had just the first power on the independent variable. Now we're going to say, well, what happens and how are things different if instead of having the first power on that, we actually have the second power on it. So we have something more of the form y equals kx squared. And how does that change everything for us? Well, to do it, let's look at this situation here. We have braking distance is the distance needed to, when you apply the brakes, how long does it take to stop, basically. So braking distance varies directly with the square of a vehicle's speed. Now if we plug in our values and solve for k, we can come up with a formula here based on the information that we have that's of this form. D equals 1/20th s squared. So that's the formula that we're going to be working with, and you'll notice once again it is a direct variation formula with a power of 2 here. So what I want to do is I want to look at the table of values here and then the graph, and you'll notice that our graph is no longer a line but now it's a curve. And the reason why it's a curve is because our rate of change is continually changing. So when we had that direct variation of the first degree, we had a line and the rate of change was constant, therefore it gave us a line. Now as the rate of change changes, it's going to give us a curve. So we could take a look at this table over here and verify that it's going to be curve instead of a line by looking at the concept of rate of change. So if you think about rate of change, if it's constant, it's got to be a line. Well, if I look at the rate of change in each of these situations, okay, so the rate of change between 2 points 10, 5, and then 20, 20, if I look at that rate of change, it's going to be 1.5. Okay, but then if I switch my points, look at say 2020 and 5125, you'll notice that now my rate of change is 3.5. So what we're saying is that that rate of change is continually changing, which always occurs with curves. Now what that means is that although we call this the constant of variation the slope when we're looking at direct variation of the first degree, if it's anything other than the first degree, that's not referred to as the slope of the line, it's just the constant of variation. Okay, so if you think about it, that you really want to think about the rate of change changing. Now we'd like to think about what this means, what these slopes mean, and kind of in words. And really what that's saying, if a slope of 1.5 is that it's 1.5 feet per mile per hour. On average, when driving between 10 and 20 miles per hour, for each increase in 1 mile per hour in speed, you will need 1.5 more feet to stop your car. Whereas when I have a slope of 3.5, it's the same idea. It's 3.5 feet per mile per hour. So in other words, now for every increase of 1 mile per hour, you have to increase your braking distance by 3.5 feet. Now, since it's constantly changing, we can only take a slope between 2 points to look at that rate of change. Finally, we'd like to take a look at some properties of graphs of the form y equals kx squared. We know that when k is not equal to 0, the graph is a parabola. The graph passes through the origin, so just like the other direct variation situations that we've already been looking at, when we look at the graph of that form, it's going to pass through that point 0, 0. Okay, it does whether k is positive or negative. Each parabola is reflection symmetric over the y-axis, which means that the y-axis is a line of symmetry for it. We know that when k is greater than 0, the graph opens up, so we can see that here. Notice how it's opening upward. And its minimum point, that vertex, will be at the point 0, 0. And then if its k is less than 0, it will have a maximum point at 0, 0, and it will open downward. Now, the domain for both of them is the set of all real numbers. However, the range, if its k is greater than 0, is going to be those values that are greater than or equal to 0. And if k is less than 0, it's going to be those values that are less than or equal to 0. Okay, and once again, it is reflection symmetric over the y-axis.